Hello guys, welcome to Friends in Tech Automation. We provide practical PLC, SCADA and IoT training. In today's video, I want to talk about PID controller. So in our previous video, we talked about the difference between open loop control system and closed loop control system. And that video is very important. If you want really to understand PID controller, kindly check our previous video on open loop versus closed loop control system. Because PID controller stands for Proportional Integral Derivative Controller. It's a feedback control loop mechanism commonly used in control systems to regulate process and systems. So actually, if you are a process control engineer, then PID is a very important topic for you. So we say that closed loop control system, the key element is that you must have a feedback. You are interested with the feedback, and the feedback here is just sensor. We are measuring the output, then we compare that output with our set point. Then we calculate what is called an error signal. So if you can check the block diagram of a closed loop control system up here, I think we did it somewhere here. This is the block diagram. You can just check our previous video of a closed loop control system. So you have error detector, so this error detector, you have controller, you have an actuator, you have a process, then you have a feedback. So you're saying that set point is your desired or reference value. So let's say that you are doing automatic level control like this here. So you want to control the level of a tank. You have to use level transmitter. It can be ultrasonic. Then you have fill valve and discharge valve, and you want your set point to be 50%. So this here fits. It's a perfect example of a closed loop control system. So you must have a set point. Let's say it's 50% or something. Then this is error detector. Then you have a controller. So controller here, in different closed loop control system, you have different controllers. So you can have PID controller for process control. You can have temperature controller and other types of controllers. Then you have actuator. So actuator can, depending on what you're controlling, you can have actuators like valves. You can have electropneumatic valves, motorized valves. You can have solenoid valves. You can have heaters. So those are just actuators. Then you have process block. Then you have output. So output here is what we are measuring. That is process variable. If you are doing level control, then level is your process, or it becomes your process variable. If you are doing temperature control, temperature becomes your process variable. If you are doing flow control, then flow becomes your process variable. So we are measuring this here using a feedback sensor, or what's called level transmitter. So this level transmitter gets the signal back to error detector. So at error detector, we compare the set point and the actual level. So when you compare those two, you can get a positive or a negative error. So that error is fed to controller. So based on control algorithms, controller will give a manipulated signal to actuator, or controllable signal to actuator. Now, I want you to imagine that instead of calling this controller just controller, let's call it PID controller. Let's call it PID controller. So instead of calling it just controller, let's be specific and call it PID controller. So we just replace here with a PID controller. So this here becomes PID controller. So PID controller is a 3-mode controller. Now I want to go deeper into theory of PID, and here I will also derive PID equation in times domain and in Laplace. Now, if you replace controller and you become more specific and you put there PID controller, then this is what we'll have here. So you have PID here. So instead of just controller, you just have PID controller. So we are giving a set point, and let's just stick with this example, level control. Okay, let's just stick with level control, where you have a tank, you have discharge valve, then you have inlet valve or fill valve, then you just want to maintain level at 50. But of course you must have a level transmitter to tell you that level is really 50. So let's just have a level transmitter here. So this is level transmitter. So this is LT, level transmitter. Your set point is 50. So your actuator is, let's just work with one here. Let's say that you are doing a manual control of outlet valve. So this is outlet or discharge valve. Then this is inlet or fill valve. So let's say that we are just doing PID control for inlet valve only. Let's say outlet valve, you are manually controlling that. So set point here becomes your desired level. Alright. So set point here becomes your desired level. So this is your desired level. So that becomes your set point SP. Then you have PID controller. So the output you are getting from the controller, let's call it controllable output. Then you take this to the process. Remember, in real systems, you must include disturbances. That's normal. You can't ignore them. But you can ignore them, but at the same time, there's nothing you can do about them, because you cannot control some disturbances. You cannot really control them. So let's not focus with disturbances, okay? So you get controllable signal, then you take this to actuator. You know you have an actuator there, then to the process. So finally the output from the process, what is called the process variable, PV, very important, PV. So here we are just checking the actual level using an LT. So this sensor here is level transmitter. Then we get to compare that here. So inside PID controller, we have an error detector. So inside PID controller, we have error detector, and we have a scaling mechanism. You can check our previous video on scaling, analog scaling, or scaling of analog signals. That's it. So let's just stick with that. So that's a PID. That's a classic block diagram of a process and a PID control. Now, if we go down here, we are saying that a PID is a 3-mode controller. That's very important. It's a 3-mode controller. So it is P plus I plus D, where P stands for proportional, controller, I stand for integral controller, and D stand for derivative controller. So it's a 3-mode controller. So if you decide to use all those 3 controllers, then you come up with PID. If you decide to use P and I, then you come up with PI controller. If you decide to use P and D, then you come up with PD controller. So you can have PID, you can have PI, and you can have PD. But we cannot have P control alone, integral control alone, and derivative control alone to control a real industrial system. So it is good to combine 3 controllers or 2 controllers to have PID, PI, or PD controller. Now, that's it and done. So what we have here, so process variable. Remember, process variable, we are getting this from level transmitter. If we stick with our example up there, then SP here is our desired level. So our desired level. So let's say that our desired level is 50%, but the actual level at the tank at the moment is 40%. So of course we have to calculate what is called an error signal. So error signal, if you go back to this here, this is the error signal, and normally we denote error signal as E of t in time domain. E of t. So this error signal is E of t. Let's just understand this. This is very important concept for process control engineers. So this error here, so error is equals SP plus or minus PV. In symbols, we can write E of t is equals SP. Normally we denote SP as R of t, that is reference, plus or minus process variable, we denote this as B of t. So that's the first equation. So that's how you can get error signal. Now this error signal is fed to three modes of PID. It will be fed proportional, it will be fed to integral, it will be fed to derivative. Then each output of this control is given to a summer. So we have a summer here. So it adds these three outputs and it gives what is called controllable signal. Now this controllable signal is given to an actuator. So it can be a valve or a heater to affect the process. That is PID. So let's dig deeper into this proportional, integral, and derivative mathematically. So proportional, we are saying that error signal is directly proportional to the output of that controller. So if you are using proportional control alone, then error signal will be directly proportional to the output of that controller. So let's just do something here very basic. So if this is your controller and this is a P controller, you are giving an error signal E of t. Then you expect an output from that controller to be U of t. So according to proportional controller, E of t is directly proportional to U of t. The only difference is that if you remove proportionality symbol here, then we have to introduce the proportional gain. We have to introduce proportional gain. So this is equals to, this equals to Kp. So Kp is what is called proportional constant or proportional gain. So error signal is directly proportional to the output of proportional controller. The only difference is that we are multiplying this here by a constant, which is called Kp or proportional gain. So if proportional gain is 10 and up here our error signal is 10, then it means the output and Kp is 5. Let's say Kp is 5 and error signal is 10, then output will be 50. So we are just magnifying error signal. All right, but what about for integral. For integral, now if we have I here, so for integral we can have I here, so it means it is integral controller. So here error signal is the integral, or output u of t is the integral of an error signal. So basically you are integrating. Oh, sorry, I think I've misled you. So for kp is the other way, not u of t is, sorry, I think I've messed there. Sorry about that. It's a good thing. So for e of t it will be kp u of t. We are just multiplying error signal. Sorry about that. But for integral here, for integral we are integrating error signals. Therefore u of t, so u of t is an integral of an error signal e of t, and since it is in time domain, then you can add dt. That is for integral. So in simple terms, for integral we are just trying to minimize what is called a steady state error. We are just trying to reduce steady state error. All right. Then we have derivative. We have derivative here, and that is d. For derivative here, we are just differentiating error signal. So u of t is just a derivative of error signal. So it is d e of t over dt. Therefore, if you increase this here, basically what we are doing, we are just improving system stability. Now, if you combine these three formulas, then you come up with this here. It's called PID equation. If you combine these three formulas, you come up with this here. So this is what is called PID equation. So u of t equals kp e of t, which is proportional controller, ki that which is now integral controller, and kd derivative of error signal, it's a derivative controller. So kp, ki, kd is what is called gains, PID gains. So normally in software, what we do, we just change kp, ki, kd. Now the process of adjusting kp, ki, kd is what is called PID tuning, okay? So what is called PID tuning. So remember, this e of t is an error signal. Let's say that your set point is 50% and the actual level is 40%. So e of t will be 50 minus 40, and that gives you 10. All right, let's give you 10. So e of t will be 10 in that case. That's it. So in summary here, PID stands for proportional integral derivative. PID is an algorithm used in a controlled feedback loop to regulate a process, such as motion of a motor or flow through a valve. So we have many theory here. This is how PID works. So the system output, also called the process variable, is measured with a sensor, what we call feedback sensor, and compare the reading to a reference value, what is called set point. If you compare these two, you get what is called an error signal. So error signal, or the comparison of reference and measured output in an error value, is used in calculating proportional, integral, and derivative responses. So these three responses are then summed to obtain the output of the controller. So the output of the controller is used as an input to the system we wish to control. So basically we feed this to an actuator or something else. So let's talk about PID controller, scalable and tunable. So scalable, we are just saying that is the sense that we can implement a simple controller by just using proportional gain or combination of the three. I think I've talked about this. So we can have PI, PD and PID. Normally we don't use P alone. So we use PI, PD or PID. Tunable, we say that the process of adjusting proportional gain, integral gain and derivative gain is what is called PID tuning. So PID tuning is done after observing your system. So you're trying to reduce overshoots, you're trying to reduce settling time, and you're trying to minimize steady state error. So those are three reasons of doing PID tuning. Now let's talk about PID curve. Very important here. This one is called PID control curve. So this is the reference here. So you have controllable variable or y-axis. At x-axis you have time. So we have reference, which is SP. So this is your set point. Then this curve here is basically what you are controlling, okay? What you are controlling. So we can call this PV or process variable. Process variable. So this here does not include the actuator, the behavior of your actuator, because in this process your actuator can be opening, closing at 20%, 30%, 40%, 50%, 60%. So it can be rising, falling, rising, falling. That's actuator behavior. But this curve here, this is for process variable, PV. So actually the goal of PID is really simple. So with PID, the objective is simple. We are just trying as much as possible to reduce the difference. If this is your SP and this here is your PV. So the work of PID is really simple. So we are just trying to reduce this error or the difference between SP and PV. We just want to minimize this. I know it is impossible to have an error signal of 0. Why? Because in a system you must have disturbances. So it's really hard to have SP and PV match. But our goal or objective is trying to minimize this error signal. And we want to minimize this error signal very fast. We don't want to take forever or a long time to minimize that error signal. So the process of minimizing that error signal is what is called settling time. And the difference here, you see this difference here? This is what is called steady state error. Your process variable, it's just swimming between your reference up, down, up, down, up, down, up, down. So you get negative error, positive error. That is what is called steady state error. So your system is not matching completely with your reference. So your process variable is not matching completely with your reference value. So whatever you're getting from your feedback sensor is not really matching completely with your set point. So it's dancing there, swimming there. That is what is called steady state error. Steady state error. Then overshoot is how much your system in positive and negative, how your process variable is deviating from your reference value this here. So the maximum, positive to negative. That is what is referred to as overshoot. Then transient state is that period of change. When you are trying to attain the set point. For example, if you have a valve and you are controlling level First time, let's say the tank is empty and you have given a set point of 50%. The first thing, logically, what will happen? The valve will open 100% to allow water in. Then when it starts trying to achieve set point, it will close down. So that process of trying to reach your set point is what is called the transient state. Then after reaching your set point, you want to maintain that set point. That's now what is called the steady state. And that is what is called PID response curve. So this lesson is very important if you really want to program or configure PIDs in TI Portal. So thank you for watching this video. If you like this video, give it a subscribe to our channel and like this video as well. So our next topic will be PID configuration and commissioning in TIA Portal. So thank you.